I know only about half of us are here that will be here, but I want to reward those of you who conscientiously come on time uh, by initiating our session. And the mic is turned on. Okay. Um, so as I thought about introducing Tom today, I first thought about examples of how I have made use of artificial intelligence, and in particular of the ChatGPT 4 program. Uh, I sometimes use it to generate examples if I need more examples of a concept. Or this past week, I used it as I was preparing for a book group, reading William James' Principles of Psychology. I was having trouble understanding the deep chapter I was in, so I asked it for a 500-word summary of Chapter 9 of Principles of Psychology, and it came back with a bullet point, plain English summary that helped me understand what I was reading. I've used it, as you can see in the handout. I mean, just to give you a couple examples, our community ministry committee was asked to brainstorm how it could be active in the community, and I asked GPT to help frame our thinking a little bit. We haven't used this. And then, just for fun, before church today, I asked it to generate a sermon based on today's Old Testament lectionary passage. Now, I don't know what Leanne Van Dyke's going to be preaching on, but if she's on this passage, you can compare her output. But you could also see how this might be useful if you were a pastor doing sermon preparation in generating some examples that you could use in building your own sermon. And Gordon tells me that he's all the time getting ads for AI-assisted sermon preparation. I've used it to generate images for my essays. So one recent essay on gratitude, I wanted a picture, an image, an original image of somebody expressing gratitude, and I shared that with my editor. She said, "This is very good, but let's make it a younger person, more informally dressed." So I went back, and it gave me some more examples that beautifully expressed the concept in an original piece of art that I could use. I've also used it in language translation. There's software now that will allow one, as I have done, to record myself on a video and then ask it to translate my minute-long message to a German person who I was needing to speak to into German. That doesn't shock you. But to do it with my face, my video, with my voice, with my mouth movements corresponding. And I've done this with my Portuguese-speaking next-door colleague, and she's just stunned that there I am in a real-life video speaking Portuguese to her. So you can think of the possibilities of that for intercultural communication, but also for deep fakes in election when words are put into Joe Biden's mouth. And finally, I decided to use it because I needed an introduction for Tom, and I'd given you my words last week. So this week, for introduction, I asked ChatGPT, what is Hope psychologist Tom Ludwig known for? And so this is the artificial intelligence introduction of Tom. Tom Ludwig, a psychologist from Hope College, is renowned for his integration of technology into teaching psychology. His journey in academia is characterized by his use of technological tools to enhance the learning experience in developmental psychology and aging. Ludwig's innovative approach includes the creation of instructional computer activities such as PsychSim, which are designed to complement traditional teaching methods by providing interactive learning experiences for students. Ludwig's contributions to the field of psychology education have been recognized through various awards, including the Charles L. Brewer Distinguished Teaching of Psychology Award from the American Psychological Foundation in 2005. His work, particularly in developing more than a dozen sets of instructional computer activities, reflects a deep commitment to improving the educational process through the use of technology. Ludwig's background in developmental psychology and aging, combined with his innovative use of technology in education, has made significant impacts on the way psychology is taught at Hope College and beyond, making him a distinguished figure in the realm of psychology education. But then I asked it to simplify that in the form of a limerick, and it came back immediately with this. In Hope College's halls, Tom Ludwig's famed. For blending tech and psych, he's acclaimed. With software so neat, teaching's made a treat. And in psychology's realm, his name is proclaimed. And then I said, that's excellent. Give me one more. And at Hope, where the winds of learning blow, Ludwig's tech and psych classrooms did grow. With Psych's hymns creation, he earned adulation and set students' minds eagerly aglow. So that's it.
Thank you, David, and thank you, ChatGPT, for that wonderful introduction. It's impressive. It's the first time that I had seen that. I haven't actually asked it to do that for myself.
Right, and if you asked it again, it would come up with a different introduction. So this was entirely unique,
as
are the outputs you hold in your lab.
So there's a certain amount of randomization built into the program to keep it from generating the same response to the same prompt. And we'll talk a little bit more about that in a moment. But what impressed me the most is there weren't any obvious hallucinations in there. It didn't describe things about me that I didn't recognize, at least in part. So it did a good job, a pretty impressive job, I think. Okay, thank you, David, and thank you again for this opportunity to share some ideas with you. If you were here last week, you heard me talk a little bit about the definition of artificial intelligence and about my view of some of the breakthroughs or significant advances in the timeline of the development of artificial intelligence. Today, and I warned you, right? I warned you this is going to be a little difficult to grasp in some parts, but I think it's absolutely essential that you not only know what the technology is capable of, but how it does it, at least to a limited extent. That's what we're going to focus on today. What makes the current version of generative artificial intelligence so much more powerful than the artificial intelligence of decades ago? What's the secret sauce that is allowing ChatGPT to do the things that David has just described? And then if you can stick around for one more week, next week, we're going to talk about the impact of artificial intelligence, the new forms of artificial intelligence on our culture, and particularly the impact on religion, spirituality, and ethics as this becomes more and more a feature of our everyday lives. Which reminds me, let's just do a show of hands. How many of you actually are using the tools of generative artificial intelligence in your work or in your hobbies or in other ways in your ordinary life? Put up your hands if you're actually doing this. Okay, I see about 10 hands or so, but all of you should have your hands in the air, right? Because if you have a phone or a tablet or a laptop computer or a smart TV, you are already using the fruits of generative artificial intelligence in your daily lives. And I'll try to explain how that all came about. Okay, now, as Dave said, we can use it just to get ideas for things. And so in preparation for this, I knew I was going to be talking about generative AI today. And so I asked a version of the OpenAI software called DALL-E, which instead of producing text, produces art. And so I asked DALL-E, generate an image that represents generative artificial intelligence. I wanted to see what it would come up with. And in about 3 seconds, it came back with 2 highly detailed, interesting pieces of art that reflect, quote, this model's understanding of the concept of generative artificial intelligence. Okay, we might not be satisfied with that, but it's a starting point. Then we could try to explore other ways of representing this concept in art. Okay, if you were not here last week, I just want to give a quick recap of what we talked about. First, I tried to make the point that all of the descriptions of artificial intelligence define artificial intelligence in relation to human intelligence. For example, my favorite one from IBM says, artificial intelligence leverages computers and machines to mimic the problem-solving and decision-making capabilities of the human mind. Okay? We're understanding artificial intelligence in relation to human intelligence. And what makes humans special? Why have humans come to dominate all the other species on this planet? It's in part because of our amazing flexibility in adapting to our environment. So intelligent humans can approach a new situation and assess it very quickly, compare it to the past, compare what worked in the past and what didn't work in the past, and understand how the new situation is different from the previous situations, devise appropriate strategies for reaching goals, and then revise or adjust those strategies on the fly if the situation requires it. That's an amazing capability. The question is, can we build machines that will be able to mimic all of these capabilities? Now, the early successes that happened in the 1950s and 1960s and into the 1970s in artificial intelligence mainly occurred, looking back now, we can see that the successes mainly occurred when researchers tried to focus narrowly on a specific problem with moderate complexity, where they could actually understand how humans would solve the problem and then build a program that would mimic the way that humans solve the problem. We call this artificial narrow intelligence, or more commonly, expert systems. So a lot of really useful work was done in that early period of artificial intelligence, building special purpose expert systems. But don't be confused. This is not anything approaching what intelligent humans can do. We're just taking one little piece of what people can do and trying to get a computer to mimic that capability. Now, the bigger, more ambitious projects failed in those early years. The projects that actually tried to build a computer that simulated the capabilities of real human intelligence. They failed because the time wasn't right. The hardware was too slow, didn't have enough memory, and the software programming frameworks had not yet been devised that could handle the level of complexity that some of these real-world problems would require. So that's changing. In the last years, and I'm going to say especially since about 2015 or 16, some dramatic progress has been made where the performance of these artificial intelligence systems has skyrocketed in what they're capable of doing, as reflected in some of the things that David just described. We're almost to the point of overcoming these limitations in the hardware and the software. And so how are these programs doing that? And what's the way forward from here? Now, stepping back, I'm not only a developmental psychologist, somewhat of a neuroscientist and computer scientist at a low level. I'm not a mathematician, and that's good for you, because otherwise I would be presenting the rest of this material today at a level that would be too high for you to understand. But I think that it's going to match what you're capable of understanding pretty well. At least I hope so. Okay, now when we look back from this vantage point in 2024, it seems to me that there's a problem of dualism that's going on. The researchers would not describe it this way, but from my perspective, the early AI programs tried to emulate the human mind. By that I mean, they tried to understand how humans think, how they solve certain problems, and then they tried to write computer programs that followed step by step that kind of human thinking. And it actually worked pretty well for simple problems where humans actually understand how we do it. If we can understand how to do it, we can program a computer to do it as well. But when we get to more complicated problems like facial recognition, nobody understands how humans recognize faces. And therefore, when you try to program a computer step by step to be able to do that, it always fails because we don't know what we're doing. Okay, and so this The new approach, and I'll be hitting this point several times, instead of trying to emulate the human mind, the way humans think and reason logically, it tries to emulate the human brain. We don't understand completely how the brain works, but we know that it's capable of doing amazing things. And so if we can write computer programs that emulate the way the brain works, maybe those computer programs can do amazing things even if we don't understand how they're doing it. Does that make sense? Yes. Okay. So this is I don't think you'll find this written anywhere else. This is my own personal take on the issue of the mind-brain problem in artificial intelligence. Now, the early years of artificial intelligence, in my view, I would call it doing AI the hard way. The hard way, because that's the only way we understood how to do it at that point. By hard way, that's also a pun, because it involves hard coding the strategies in the program itself. So remember, this early approach tried to solve problems by teaching the computer to do things the way that humans would do them. And so first, you need to pull together a team of cognitive scientists to try to analyze the problem and figure out how humans are doing it, how humans are coming up with the correct solution. Then we hire a bunch of programmers who try to convert that sequence of logical steps into program code, and then if you run that on a program, the program appears to be intelligent. It has artificial intelligence that was built into the program, hard-coded into the program, that does the process the way that humans think it should be done, the way that humans would do it in their own mind. So, for example, Alan Turing, I talked a lot about him last week. If you weren't here last week, he's one of the heroes in the story of artificial intelligence. For all intents and purposes, Alan Turing invented the modern digital computer. Even before it could be built, he invented the idea of the digital computer before World War II. And then you're familiar with some of his successes in code breaking during World War II. And then after World War II, he was put in charge of England's very first large digital computer, which was being run at the University of Manchester in 1947, 48, 49. And he was in charge of the software. He wrote the software that allowed other people to write software for this computer. And his very first computer program was a long division program where he taught the computer, and this was a very laborious process. Initially, the program had to be entered not one line at a time, but one instruction at a time by pushing levers and then inputting that, and then pushing levers and inputting that, pushing levers, inputting that. He wrote a program that could do long division the way that people do long division. So this was an artificially intelligent system. It could mimic the capabilities of the human mind, but it wasn't a very efficient process, but it worked for simple problems for which a clear strategy exists the way humans would do it. Now, why couldn't we scale that up? Why couldn't we use that method to solve all the problems that would make it possible to have a computer with artificial general intelligence? Well, one issue has to do with understanding the problem. It's very different. The more complex the problem, the harder it is to specify the rules for solving that problem, right? And so we run into a problem of knowledge. The cognitive scientists don't really understand how humans solve the problem, therefore we can't program the solution. Secondly, the program in itself is tremendously time-consuming because you have to build all the intelligence into the program. And human computers, human programmers make mistakes. And so you have to continuously debug. The more complex the program, the more mistakes and the harder it is to debug the program. And then you get it to work perfectly on a particular problem, and then the problem changes slightly and the solution no longer works. Okay, now we need to start over, right? We need to adjust the program by hand using the computer programmers again in another time-consuming process to rewrite the program. Now, I'm going to give you two examples, not as models for how it should be done, but models for how it was done in the 1970s and 1980s on a small scale. So back in 1981, I did my first AI expert system. I was doing research on left-right hemispheres of the brain, and I wanted a system that could speak simple words into one ear or the other ear. And so I got two Z80 computers. You probably never heard of them. This was before the IBM PC. And a couple of specialized audio synthesizer chips that could make any sound that I wanted to make. And what I wanted to do was teach the computer to be able to speak a limited set of three-letter words that all had the form consonant, vowel, consonant. And then also, and this was a harder problem, trying to get it to recognize when a human spoke those same words. Now, the problem here is, I mean, we knew how to do this back in 1981. We knew the speech waveforms, and we knew how to program the audio synthesizer chips to create any speech, any waveform that we wanted. But you had to specify the frequency or pitch of each moment in the waveform, and you had to specify the duration that that particular frequency gets expressed through the speaker, and so on. And so the speech waveforms are extremely complicated waveforms to build, and when you're trying to do it one little piece at a time, it's very time-consuming. And the other issue was that it was difficult to expand the system. It actually worked, and Dave might not remember it, but in May of 1981, I demonstrated this for the psych department. This computer that could speak individual words on command. Now, it wasn't practical because it didn't scale. The computer itself, although it was the most powerful microcomputer, the most powerful personal computer that you could buy in 1981, it wasn't powerful enough for this task. The hardware, it wasn't fast enough, and it didn't have enough memory storage. And the software to develop this was in an early stage, and so there was a lot of extra work that today's programmers don't have to do because there's intelligence built into the programming languages that wasn't there back in 1981. Okay, that was an important learning lesson for me, and I realized that no matter how much work you pour into a particular problem, if it won't scale, if you can't add more, it can't broaden the scope of the program, it's probably not going to be ultimately successful. So in 1985, I tried a different approach, and I built a small system that was a chatbot. Remember Eliza, the chatbot? I called this Computer Therapist, and it was an attempt to model Rogerian non-directive therapy. Some of you are familiar with that type of psychotherapy. It was, of course, based on the Eliza work that Joseph Weizenbaum had done in 1966, and just like Eliza, everything in this program was hard-coded by hand. And so this program was designed for college students to use. So I modeled the keywords in the program on the life experiences of college students as best as I could figure out what kinds of things were on their minds. And I wrote 3 appropriate responses for each keyword, and then there were some generic responses for statements in which there was no keyword. And so this program was a pattern matching form of artificial intelligence. So when a student typed a statement, my program cycled through the words in that statement one by one, comparing each word with my list of keywords. And if it found a match, then the program then delivered one of my 3 appropriate responses to that keyword. And if it couldn't find a match, then it tried to do what's called reflection. And that's what Rogerian counselors do, right? They're supposed, you tell them your problem, and instead of them giving you the answer, the solution, how you're going to fix that problem, they simply reflect back your feelings to you so that you can solve your own problem. That's okay, you didn't need to know that. But what you did know is if there was no keyword match, my program tried to reflect back what the student had said. And if it was not possible, because of the grammatical constraints of the sentences, if it wasn't possible to make an appropriate reflection, then my program fell back on the default generic statements just to kind of keep the conversation moving. So before I show you a sample dialogue, I need to explain a little bit more about what this means in a programming logic to do a reflection. And so you probably can't read this very well, but the reflect rule for I am or I'm at the beginning of a sentence, you simply strip away the I am and keep the rest of the sentence, the predicate. And then you replace the I am with how long have you been, and then you print the predicate. And so it looks like this. I'm feeling pretty discouraged. If you get rid of the I'm and replace it with how long have you been, you can just print the predicate again, and it sounds like the computer is responding to what you said, understood what you said, and is asking you an intelligent question about what you said, but it wasn't an intelligent, it was quite a response at all. It's a pre-canned response using this reflection technique. So now we're going to quickly take you through a sample dialogue, a short one. Okay, the computer asks, what's on your mind today? And the student types, I'm feeling pretty discouraged. Well, that wasn't, my 80 keywords are not in that. And so now we need to reflect, try to reflect that statement. And the reflection is, how long have you been feeling pretty discouraged? So that prompts the student to type another sentence. Well, it's been a while. Okay, that's not very informative. Sounds like a college student, right? It's been a while. And so because there's no keyword, we have to do a generic response like, I see, tell me more. Okay? Does that sound like a Rogerian therapist, right? Just, yeah. So trying to prompt you to go deeper into this thing. Okay, and so then the student plays along for a while and says, I'm really worried about my grades. Well, grades in an academic setting is one of my 80 keywords. So I've got a canned response already to go into the response. Yes, that's a common concern for students. Is your academic performance important to you? So that sounds like a realistic conversation. And the student says, very important. Even more important to my parents. Whoa, okay, parents is another one of my 80 keywords. So I've got a canned response, your parents. Now, without knowing anything about what the problem is, my canned response says, how do you think they feel about what's happening? So the student thinks that the computer knows what it's talking about. The computer doesn't know what it's talking about. It's just giving this, it's not a generic response, it's a response appropriate to that keyword parents. And the student says, they're definitely upset with me right now. I should have had upset. Upset should have been one of the keywords, but I didn't think that far ahead. And so I had to reflect it. Now notice that the they are has to be flipped to are they, and the me has to be flipped to you. That's what computers are good at. Finding the pattern, substituting one thing for another thing. It works, okay. Okay, I guess I'm a disappointment to them. I did have disappointment in the list. Can you say more about the nature of this disappointment? Again, the computer doesn't know anything about what the student is saying other than the student used one of the magic words. And then the student is backing off now. They think this might be being recorded somehow and it's going to be sent to their parents or whatever. And so not really. And there's no way I can respond to that other than with one of the generic responses. Let's move on, okay? And then the student is getting tired with this and says, I'm getting bored. And bored, I had enough forethought to put that into the keywords. And so what do you typically do when you're bored to try to get them to hang on a little bit longer, but the student was having none of it. The student was done and said goodbye, which is a keyword. And then that prompted the program to, say something nice about our time together, and then the thing is done. Does this make sense? Can you understand how you can use this form of hard-coded programming logic to give the illusion that the program is actually having a conversation with you? And some people are actually caught up in this for a little while, but after a few minutes, the novelty wears off and you can begin to see that the computer is making nonsense It's reflecting back things that don't really matter and not picking up on the things that did matter. And so but for a 5-minute exercise, it's a really effective exercise in the power of artificial technology, 1985 era. Okay, now, the projects that I was engaged in were small scale. But other individuals and companies were using the same processes, only they were in a position to pour a lot of money into the process to build a better hardware and to purchase a lot of really good programming talent and invest lots of hours in doing this. And they had considerable success with building expert systems using this hard way of doing it. So for example, in 1963, the post office introduced zip codes. And almost immediately, they tried to build a computer system that could read handwritten zip codes. And that turns out to be really difficult because there's so many variations in the way that people write numbers. Think of the number 4, all the different ways that you could write the number 4. And then you add in the fact that some people write in a slant this way, and some people write in a slant that way. Some people use a thick marker, and some people use a thin pen. And so trying to build in all the programming rules that can recognize all of these variations makes it a difficult problem. But the post office had money and resources, and they kept throwing money and resources at it. And after about a dozen years, they had systems that were pretty good at doing this. Just that one limited thing. This is not intelligence like humans. It's an expert system focused on one task. The same thing with Bell Labs. They came up very early on with a way, like I was doing, of using computers to synthesize human voice. And before long, they had a pretty good expert system that could read out a telephone number in a robotic voice. You remember that? 396, so on. That was an expert system dedicated to doing nothing except converting a number, a digit, into a voice waveform. But as long as they were using these brute force methods of hard coding, trying to anticipate every possible outcome, the programs got bigger and bigger, more complicated, more errors were introduced. They made little progress towards real artificial generative intelligence of the kind that's in your phone today. And so this takes me back to something I mentioned the first session, Lady Lovelace's objection made before the first 100 years before real digital computers were available. She anticipated the fact that as long as we know how to do something, we'll be able to write a program to teach a computing machine to do that. But that isn't thinking, because as long as computers are only echoing or repeating what they've been programmed to do, they have no originality. Before we can start talking about computers thinking or having intelligence, we have to be able to show that they can originate things that go beyond what logic was programmed into them. So I agree with that. But another hero in the story of AI is a man named Jeff Hinton. I'm going to show you a little clip of him later. But a famous quote of his says, if you want to make a device do something intelligent, you've got two options. You can program it, which is the hard way, or it can learn. And that's the new way of doing things. Okay, so my view about the remarkable shift that's happened in the last couple of decades, and especially since 2015, is that it represents a mindset shift, a fundamental shift in the way people are approaching the problem. And Jeff Hinton is one of the people that pioneered this approach. Moving away from programming the strategies to do the task and towards programming the strategies for learning how to do the task. That is a completely different way of approaching the problem. Now, this would never have been possible using the computers that were available in 1980. And so we have to recognize that this shift in the perspective of how to solve the problem was made possible by the tremendous decade by decade increase in processing speed, in memory, and in the software architecture that allows programmers to be efficient in controlling all of this power. That's what underlies it all. And so, to go back to Jeff Hinton's quote, instead of programming, let's teach the system to learn. And to do that, we need to step back, maybe take a little detour, and think about how it is that people learn and how it is that children learn. And so remember, back in the 1950s and 1960s and 1970s, in the research labs across the country that were working, and around the world, a lot of this work was done in the UK and Australia and Canada, and some in Germany. But wherever there were research labs working on AI, there was a team of computer scientists that were working on the hardware and software, and there was a team of cognitive scientists that were trying to look at how humans think and solve these problems, and they were working together. The cognitive scientists were influenced by a famous Swiss psychologist named Jean Piaget, who came out with a theory about how children learned that turned out to be tremendously influential in the broad picture of artificial intelligence. Piaget's theory, and it's a long theory, but I'm going to give you a synopsis here, is that the growth of intelligence in children requires that they have the raw materials somehow, the structure, the building blocks of information, and the name that he gave to the containers that hold that information is schema. So the way I want you to think about this is like a schema is like a pigeonhole or a box or something like that. It holds information, and the information in that box can be used to solve a problem. And so what's in the box could be a mental representation of an idea, a concept, or what's in the box could be a mental representation of an action pattern, something that you do. So knowledge and skill. The Greeks called it gnosis and praxis, right? Knowledge and skill. It has to come together in order for intelligent behavior to emerge. So the knowledge is held in these structures called schemas. Okay, now, so let's take the case of a 5-month-old infant just barely working on learning to sit up, maybe with some support, maybe by itself, and it's discovered that there are interesting things in the world, like this star. And so one of the things this child wants to do is touch the star or grab it and then eventually put it in its mouth. But first it has to get the hand to the star. That's called a reach and grasp motion, and children are not born with it. They acquire it slowly between months 4, 5, and 6. By 6 months, most infants have a reach and grasp schema, an organized pattern of behavior to be able to perform this task. So how did they get that schema? So remember, the growth of intelligence requires the raw materials plus ways of acting on those raw materials. And that's what Piaget called the functions. And Piaget believed the most important functions were assimilation and accommodation. So basically, when you're assimilating, and we're doing this, not just children, it's all through our lives. When we hit a new problem, we first try to use our existing understanding as is. We apply our existing schemas to the new situation, or another way of thinking it is we assimilate the new situation into our current understanding, what we're capable of understanding and doing. That's assimilation, using schemas as is. Accommodation, on the other hand, is modifying or adjusting our schemas in response to the environment, the requirements of the environment. So now we're going to try to make a math model to represent the reach and grasp schema. So now the child's facing away from us because it'll simplify things. The star is in a fixed position, and the child's hand is down by his side, and now the child is going to want to touch that star. How are you going to move the hand from its current location to the new location? Okay, so in this three-dimensional system of coordinates down in the lower right, we're going to represent the child's hand position by using 3 numbers, x, y, and z. The x number, that value of x, is the horizontal location of the child's hand. The y number is the vertical location of the child's hand, and the Z number is the depth, how far the child's hand is away from the body. Okay, so the initial position circled in red, we're going to call that X, Y, and Z. So the position P is a function of those three numbers. Now, what happens when the child tries to change the position of the hand to reach for the star? Now we have to add an offset to each of those values. So I have my hand down here, and that's the starting position. And now I want to raise it up. That's going to be the y-axis. So we have to add a positive offset to y. I need to move my hand a little bit to the left. That would be adding a negative offset to x. And then I need to extend my hand. That would be adding a positive offset to z. So we can express or represent the new target position, the desired outcome of the reach and grasp schema, as a function of this new set of numbers. The original position, x, y, and z, with each of those positions offset by some value, which we're calling V1, V2, or V3. Are you with me so far? Okay, now, according to Piaget, once a child attempts an action, the child continues to practice that action over and over and over. And if you watched a baby doing this, throwing a rattle down, picking up a rattle, doing things again and again and again until they master that particular task. Okay, then once it's mastered, it goes into one of those pigeonholes, one of the boxes. It's now an organized pattern of behavior. It's like a computer program. So anytime the child wants to do that, it can just pull up that computer program and run it, and it can perform that action. Now, that's a schema. Now it has the schema, and that means if the next day we bring the child back, put the star in exactly the same position, the child can simply assimilate. The child can use the existing reach and grasp schema as is with no changes, and it works. The child gets rewarded for using assimilation. But what happens when we move the star to a new location? The schema doesn't quite work anymore. It doesn't give the desired result. And so what the child needs to do is to adjust the schema, that's accommodation, right? So that the child now can get the hand position to the new target location. And what that means in this kind of mathematical model is the child needs to adjust the offsets, right? The child's not thinking this way, right? The child doesn't know anything about math. But we can think, because now we're thinking already about building a robot arm that can do what the child is doing, to reach out and touch a particular spot on a board in front of it. Okay, and so in this math model, we need to change the offsets, V1, V2, V3, in order to be successful. And we can say now, and using Piaget's words, the child is smarter than before. This represents the growth of intelligence, that this combination of assimilating, using schemas as is, and then accommodating when we need to make adjustments, that twin process is how through life we grow in intelligence. Okay? This is important stuff, and it was very influential in these research labs. Now, the key here in learning is you need to get feedback. For the child, the feedback comes through the eyes. So the child reaches out and misses the target. The child can see that the target is over here. My hand went there, the target's here, and so now I need to adjust my reach and grasp so that it hits the target. But when we're talking about the robotic arm, where's the feedback coming from? Well, we need to build in sensors that can provide feedback to the system about how much the arm missed the target so that we can gradually improve. Now, from here on, I'm going to flip the equation because it'll be easier for you to understand. Instead of putting t at the beginning, we'll put t at the end. So that's the outcome. So what we want to do is be able to represent this new target position as a function of the old position, x, y, and z, with an offset added to each of those parameters. Now, when you think about it, adjusting the offsets is what we mean by the AI system learning. It has learned to improve its performance by taking the feedback about its error and adjusting these parameters. Now, I've been calling them offsets because it made sense in that three-dimensional space. I'm going to shift over to the terminology that's used in AI systems and call these weights. So we always start out with some value, a set of values, and now we're going to adjust those values, and rather than adding them in current AI systems, it's always multiplying them. We multiply each value by a weight, and we get a new value, which then represents progress towards better performance. The system is learning by adjusting those weights. Let me say that one more time. What is the learning that the child does in improving the reach and grasp? The learning is adjusting the position of the hand in that three-dimensional space, and that's the same thing as the robotic arm adjusting the weights that are applied to each of the old values to get us to the new value position. Now, early attempts at AI failed in part because all of the intelligence had to be put into the program at the beginning. And so if the situation changed, the program couldn't respond to it. Now, using Piaget's terminology, these early artificial intelligence systems could assimilate. They could use the schemas, the knowledge, the patterns that had been programmed into them, but they couldn't accommodate, they couldn't adjust those patterns in response to the new situation. And so for a while, one possible solution was thought to be, we can hard code the feedback loops into the system. And so, for example, if we have a robotic arm and the robotic arm misses the target by 2 inches, let's program that in. And so figure out whether the target is to the left or the right of the arm. And then if it's to the left, adjust left by 1/4 inch and try again. And then if it's still not right, adjust another 1/4 inch and so on. All this intelligence for adjusting the weights is programmed from the beginning into the system. But you have to be able to anticipate what kind of errors the system is going to make in order to hard code ways of responding to those errors. Not a good long-term solution. The solution was to give up the idea of emulating the mind, of emulating the way humans think about the problem and would solve the problem. And instead switching over to trying to emulate the brain by building what are now called artificial neural networks. Now, the human brain is very complex. In fact, it's the most complex structure in the known universe. We believe that it has about 86 billion neurons or nerve cells, but about possibly 100 trillion synaptic connections between the different neurons. That's an amazing number, okay? 100 trillion connections. Now, we can represent those connections by using a diagram, and you'll see this again and again if you look at neural network reports, that the neural network is usually arranged this way, where each of the circles in the network diagram represents a neuron. Okay, in artificial intelligence work, we call this a node, but it's basically a neuron. And that neuron has an activation level, which you can think of as how excited it was. And then each arrow in the system represents a connection, what we might think of as a synapse. And that connection has a numeric value too. So if the numeric value of the node represents how excited it is, the numeric value of the connection is the weight. How much weight should we give that activation as we move to the next level of the system? And then each vertical column represents a layer in the artificial neural network. Now, I've got a very short video clip that I hope will explain it a little bit better. So
first, you should understand that an artificial neural network, also called neural network for short, is at its core a mathematical equation. No more, no less. A powerful neural network is typically a very complex equation, but nevertheless, it's just math. The term neural network comes from its analogy to neurons in our body. In our brain, we have around 86 billion neurons. These neurons are what give us the ability to do anything. They send the signals to the various parts of our body to act, and they send signals to our brain that can enable us to think and be humans. Neurons and neural networks serve an analogous role, and that's why the nomenclature is similar. But let me stress this from the start. Neurons in our brain are much more complex and advanced than neurons in an artificial neural network. Artificial neurons do not work the same way. The analogy with artificial neurons is limited because it applies to the way that they are networked, not to the way that they function. Like in the brain, we connect multiple neurons together and form a neural network which we can train to perform a task. If we continue the analogy a little further and look at a biological neuron and that in an artificial neural network, we see why it makes sense to draw this comparison. A biological neuron has a cell body with a nucleus. This is the core of the neuron where the processing takes place. Around the cell body, there are dendrites, which are signal receivers. They take in inputs which the cell body can then process. On the other end, there is an axon, which ends with the terminal axons that can pass on a signal to the dendrites of the next neuron. In a similar way, a neuron in a neural network is a processor, which is essentially a function with some parameters. This function takes in inputs, and after processing the inputs, it creates an output, which can be passed along to another neuron. The input is analogous to the dendrites, and the output is analogous to the terminal axons. The function in the neural network is like the cell body. Like neurons in the brain, artificial neurons can also be connected to each other via synapses. This is what a neural network is. It's neurons connected with each other, receiving inputs and passing along outputs in a complex network. While an individual neuron can be simple and might not do anything too impressive, it's the networking that makes them so powerful. And that network is the core of artificial intelligence systems.
Okay, did that help? So you can see why the idea of neural networks works when we think about artificial intelligence systems. Now, so just to recap, when we look at a diagram, each circle is a node representing an individual neuron, and it has a numeric value representing the activation level or how excited that neuron is. Each arrow represents a connection that shows something about the strength. How much weight should we give the inputs from the previous layer? And that is a numeric value. The weight it's easy to understand. The bias is a little bit more difficult, so I'm going to stop talking about biases. It's part of the formula, but we're going to treat it as though we're only talking about node activation levels and weights connecting each node to the layer that's beyond it. Okay, and each vertical column then represents a layer. And so the minimum number of layers would be 3, because we'd need an input layer to receive the information from the outside world. We need an output layer to make a decision about what happened. And then we need a hidden layer, which is going to be where the computations happen that we don't fully understand, but we know will give us the output that we need. Okay, let's look at a quick example. In this case, we're trying to build an artificial neural network to detect where a dot of light falls on a screen. And so in this system, we have the input layer activation. This input layer in red is receiving its input from a set of light meters that are focused on each part of the screen. And so the top one, that's getting a value of 7, is picking up the average brightness of the left part of the screen. The bottom one is picking up the average brightness of the right part of the screen, and the middle one is kind of a fudge factor. It's picking up the brightness in the middle of the screen. And so we can see that the top node, the one focused on the left, getting input from the light meters focused on the left, is going to be more activated because there's more energy on the left half of the screen. Okay, then there are weights which translate those values into the next node. And so that number 8 at the top is the weighted average of 0.7, 0.3, and 0.2 multiplied by the weight that we've assigned to each of those nodes in that. And so we've got each of those, the 0.8, 0.6, 0.3, and 0.1. We're already starting to see some intelligence in the system in that the top nodes those values are higher than the bottom nodes. And then if once we, once again, take the activation in each of these nodes in the hidden layer and multiply it by the weight that's been assigned to each of those nodes, that this number is the weighted average of all of its connections from the previous layer and so on. And now the output is clear. The output node that's associated with the left side has a higher number. It's more excited. It's got more activation. And so the decision of this neural network would be, it's probable that the light is falling on the left side of the screen. See how this works? Now, this example is taken directly from a famous project that was begun in 1956 at Cornell University by a guy named Frank Rosenblatt. And my three heroes in this whole story, Alan Turing was by far the most important person in the early history of artificial intelligence. But between the mid-1950s and the mid-1960s, when a lot of important stuff happened, I think Frank Rosenblatt was probably the most influential and important person in that era, because he's the first person to actually implement the idea of an artificial neural network in a way using a computer system that worked. Now, this computer system filled an entire room, so it wasn't a real practical kind of system, but it actually worked. And it worked in the same way that I just showed you, where he was able to design this system so that if you projected the letter X onto the input receptors of this light meters of this system, and that activation was then passed through to the electronics connecting the hidden layer, and then passed through again by multiplying those weights to the output layer, his system, which he called perceptron, was actually able to recognize a limited set of letters. It worked, and he did it not by hard coding everything into the system, but by hard coding the process by which the system could set up the weights and come out with an output which was accurate. Now, this is where I came into the scene, because I started graduate school in the early 1970s, and at that point we spent a lot of time studying a model that flowed out of Rosenblatt's approach. And the model was called pandemonium. That's a pun, because this model conceptualized each layer of the network as a set of tiny demons that are running around in your head. And that at the input layer, the letter R is being projected on the input demon. And the first hidden layer, you can't read it, but it says feature demons. Each of those feature demons has one job, and that is to get the input and try to break it down into its component parts. And so this top one only responds to vertical lines. The next one only responds to horizontal lines, and so on. We know there are areas in the brain's visual system that actually do this, that are feature detectors. So this made some sense biologically. Now notice that the one on the bottom is looking for circles. And there are no circles in an R, no perfect circles. And so it's kind of lazy. It's not getting activated. It's just doing nothing. Whereas some of the other ones that are processing vertical lines and horizontal lines are pretty active. So in this pandemonium model, neurons, these demons, express their level of activation by yelling. And so some of these are yelling more than others. And so then the next layer, in the hidden layer, we call them cognitive demons, and their job is to try to match up the features with their own letter. And so we have a letter here, D, and it's getting kind of excited. It's starting to yell because the R input contains similarities to D. And the letter F, it's yelling as well. The letter P is yelling. But of all of them, the letter R is yelling louder. And so now we get to the output layer, and there's a decision demon there that's trying to, this is the weighted average of all of the previous inputs, and it's deciding that the input must be an R because the R cognitive demon is yelling louder than all the rest. So pandemonium, everybody's yelling at once, but some of the voices are louder than others, and that represents activation and how we get from from the input to the output. Okay, I'm almost out of time here, but I want to mention two more things before we quit. So what we've been talking about is forward propagation, also called forward pass. So the inputs come in at one layer. There are weights which then transfer the activation of each node onto the next node. And then finally we get the output layer, which makes the decisions. At the output layer, the node which has the highest level of activation is the one which is going to be selected as the decision of that network. Now, the most fundamental thing that happened in this whole process of using neural networks happened in the mid-'80s when an idea called backpropagation was introduced. Now, backpropagation had actually been discovered independently a couple times in the 1970s, but nobody did anything with it. In 1986, David Rumelhart and Jeff Hinton published a paper which brought this to the attention of all the rest of the artificial intelligence community, which provided for the first time a method of calculating the error, the difference between the desired outcome and the actual outcome, and feeding it back through each of the layers of the artificial neural network and adjusting each of the weights. And the point here is, for the first time with backpropagation, we had a mathematical equation that could allow us to turn the computer loose, turn the system loose, and it could work through many passes: forward pass, backpropagation, correcting the errors, forward pass, backpropagation, getting better and better at each pass without any further intervention on the part of the programmers. So we're finally past Lady Lovelace's objection, because now we're getting an AI system whose performance goes beyond anything that could be programmed directly into the system. I need to stop now, but there are still a few things I wanted to talk about in terms of the details here. ChatGPT, how does that work? I'll start our session next week with that particular issue.
So say just a bit more about what you anticipate for next week. This has kind of been a deep dive under the hood of how the car runs today. And next week we're going to talk not only about the practical systems today, but also their application and threats for the church and for personal ethics.
Right. So what I'm hoping to do next week is talk a little bit about the superficial ways in which AI is going to affect the workings of the church and its ministries, and how it may enhance some aspects of people's own personal Bible study and spiritual life and education in religious topics and so on. But then also think about how AI is going to pose a threat to culture as a whole, to humanity as a whole, but also to religion in terms of supplanting, taking the place of some of the things that people turn to religion for, to meet some of the needs that religion can meet. And so I hope we have more time for discussion next in the final session, and I hope you'll come back to hear the rest of the story. Thanks.
Great, thanks.